get is being evaluated at root 9 minus b and at 0. And once again, I'm just doing this whole problem over again a second time using a totally different method. This is the equation I'm trying to solve, right? For what value of b is the area of that red region equal to 9. And I guess if I do this, it just works out, right? So now plug root 9 minus b in for x, and I get negative 1/3 9 minus b to the, well, because that's 9 minus b to the 1/2, when I cube it, I get 9 minus b to the 3/2. And now I am multiplying 9 minus b by another root 9 minus b, which is again 9 minus b to the 3/2. Maybe it's maybe I do this in, since seem to be doing this in 2 steps anyway. This is like root 9 minus b quantity cubed, but then each of those are just 9 minus b to the 3/2. So this becomes negative 1/3 9 minus b to the 3/2, plus this is also 9 minus b to the 3/2. And now we see, I think, that what we end up with is 2/3 9 minus b to the 3/2 equals 9. And now we're back at the same point again that we were earlier, right? Multiply both sides by 3/2 and you're back here. So this is indeed another way to solve this problem. And there's even another way to solve this problem, I suppose, which is to find the area of the purple region. But how are you going to find the area of that purple region? Well, you have to do it horizontally, because now there's no consistent vertical rectangle which will take you all the way from the left edge to the right edge of that thing. And so the other way to do this problem, I guess this is the third way, that should also work out, would be to integrate up the y-axis. This would have been probably easier than what I did over here, I'm not really sure. From 0 to b, yeah, this was easier. They take the integral from 0 to b of, up the y-axis of root 9 minus y dy. And, okay, maybe I'll just very fast do this. Can I squeeze it in? I bet I can. Using this exact same substitution, I get that this will be the integral from when y is 0, this is 9, and this is root 9 minus b, and this will be, I need to put in a negative and undo the damage. There's a negative outside here, and then this is, I'm just back at the exact same spot again. The only difference is, well, there's like almost no difference, because here I get from b, instead of going from b to 9, I'm just going from instead of going from b to 9, I'm going from 0 to b. But when I change my limits of integration right now on the very next step, when y is 0, u is 9, and when sorry, that was garbage. When y is 0, u is 9, and when y is b, u is 9 minus b. So it's actually not the exact same thing. It's what I get is the integral from 9 minus b to 9 of root u du. And okay, and just finishing this off in this tiny space that remains, that gives me 2/3 u to the 3/2, but then evaluated at 9 and 9 minus b. And that's what I want to be 9. But when I then just stick all that in, what do I get? 2/3. Well, u to the 3/2 is 27 minus, what happens when I plug 9 minus b in there? Well, I get 9 minus b to the 3/2. This is not better, I guess. And so I get that. But then that gives me 27 minus 9 minus b to the 3/2 equals 27. Equals 18. Oh man. 9 multiplied by 3 halves. 9 times 3 halves. No, that is going to give me 27 halves. But then, okay, then on this final step, what do I get? Is I get 27 halves equals 9 minus b to the 3 halves. So again, it's the same equation. Star, star, star. Okay, so 3 seemingly totally different ways to attack this problem. Find the area of the purple region by drawing horizontal rectangles integrating up the y-axis from 0 to b. Being very careful with your integration and changing your limits as you go gives me this star down here, which is the same as what I get if I try to find the area of the red region with vertical rectangles going from 0 to x equals 0 to x equals root 9 minus b, or finding the area of the red region going from b to 9 up the y-axis with horizontal rectangles, which is what I did first. And all 3 of those lead to this kind of weird equation right here with the star, and they all have solution b should be 9 minus 9 over cube root 4. So in fact, it's the line y equals 9 minus 9 over cube root 4, which divides this region into 2 equal regions. Okay. Good. 2 more to go. 2 more to go. Let's do it. Oh, crying baby. '93 and 94. 93 says, find the area between the graph of y equals sine x and the line segments joining the points 0, 0, and 7 pi over 6 negative 1/2 as shown in the figure. Okay, so I think this problem is not really deep or anything. We have some points 0, 0. We have our sine function, which does what sine does. That kind of thing. That's 1. And then, so that's like pi. But then, if you go over here to the point, oh, and of course sine continues. But when you take sine of 7 pi over 6, what do you get? You get negative 1/2. And that's just a fact of sine. Yeah. So now they say connect those 2 points together and let that line from the origin to that point, let that mark the boundary of some kind of region. And so this is the region that we're trying to find the area of. And how can we find the area of this region? Well, I think it's pretty straightforward. We will split this up into rectangles, and these rectangles will look like this. So for arbitrarily chosen x value, what's the height of that red rectangle? The top is always determined by the value of the sine function. The bottom is always determined by the value of the line. Okay, well, what's the equation of this line? Well, it's like y plus 1/2 equals, sorry, what am I doing? The slope, well, this line goes, in fact, through the origin, so this is just going to be in the form y equals mx. I can use this sort of 0, 0 point. But what's the slope? The slope of this line is, well, the change in y is negative 1/2 from here to here, and the change in x is 7 pi over 6. So whatever negative 1/2 divided by 7 pi over 6 is, let's see, 2's cancel, and we get negative 3 over 7 pi, I guess. Okay, so, therefore, this is in fact just the line y equals negative 3 over 7 pi x. That's what algebra 1 tells me is the equation of this line. And therefore, the height of this representative red rectangle will be the y-coordinate of the sine function minus the y-coordinate of the line, which is negative 3 over 7 pi x. And I take the length of that red thing, I multiply by the thickness, and I integrate from 0 to 7 pi over 6. I don't think I've ever done this problem before. Okay, so this is the integral from 0 to 7 pi over 6 of sine x plus 3 over 7 pi x. It's a little bit of a silly problem, to be honest. Okay, so what's the antiderivative of sine? It's negative cosine, I guess. And the antiderivative of this is going to be upper power divided by 2. So this should be plus 3 over 14 pi x squared. And all of this is evaluated at 7 pi over 6 and 0. Okay, let's do it. Cosine 7 pi over 6 is negative root 3 over 2. So that's root 3 over 2, root 3 over 2 plus, and then there's just this disgustingness. I don't know what this is. 3 over 2 times 7 pi, but then there's just like another 7 pi over 6 squared. So here's a 7 pi, here's another 7 pi, and then there's like a 36 down there. Okay, sure. And then minus cosine of 0 is 1. So that's negative 1, and then that's 0. So when all of this clears, what do I get? Root 3 over 2 plus, that cancels, then, yeah, I can cancel that 3, becomes 12 down there. So like 7 pi over 24 plus 1. This is kind of a stupid problem. But I think that's my answer. Root 3 over 2 plus 7 pi over 24 plus 1. That could easily be wrong. Let me check this really quick. Check of this. 93, eh? Root 3 over 2 plus 7 pi over 24 plus 1. Yeah. Okay. Good. That was 93. 94. Last problem from this section. And kind of exciting. Here it says, oh, dude, just find the area of an ellipse. So that's kind of exciting. So I have some ellipse. And this ellipse is horizontal. Here's a comma 0. Here's 0 comma b. And I want to find the area of this ellipse. Okay, first of all, the answer to this problem should be just obvious. Because what is an ellipse? It's just a stretched out circle. And I know that the area of a unit circle is pi. And if the area of a unit circle is pi, then what happens to a unit circle when I stretch it out horizontally by a factor of a and vertically by a factor of b? Well, the area is going to increase by a factor of a when I stretch it out horizontally by a factor of a, and it's going to increase by an area of by a factor of b when I stretch it out vertically by a factor of b. And so definitely all common sense suggests that the area of an ellipse should be pi AB. Yeah. So keeping that in mind as the answer I expect, let's just go do this problem. So what we have is this an ellipse, x squared over a squared plus y squared over b squared equals 1. And now we're going to do it. Okay, well, I think what I'm going to do is just do a quarter of it and then divide, or multiply by 4, I mean. So this is the point 0b, this is the point a0, and I'm going to find the area of this region. And I'm going to find the area of that region by splitting it up into a bunch of rectangles. It really doesn't matter whether I draw the rectangles horizontally or vertically, so I'll just draw them vertically. So I pick an arbitrary x value and I need to find the y value. Well, for that I need to just solve for y. So this is the kind of thing we did back in pre-calc. So you get, y squared over b squared equals, and then I add this over to the other side, so that's like, x squared plus well, it's 1 minus x squared over a squared. Sorry, I was trying to do too much in my head. But then so then that gives me y squared equals, this can be simplified to a squared minus x squared over a squared times b squared. And so what I end up with is that y is in fact just b over a root a squared minus x squared. That's just doing some basic algebra to solve for y. Alright, so then the setup, at least for this problem, shouldn't be too hard. I just need to take the integral from 0 to a of a bunch of things. Well, I take the rectangle, which has height b over a root a squared minus x squared for a particular x. I multiply by the thickness of that rectangle, which is dx, and I add up all those areas by integrating from 0 to a. And then I multiply by 4 because this is just a quarter of the full ellipse. Alright, so I pretty much immediately find myself in this situation where the answer is 4b over a times whatever the integral from 0 to a is of root a squared minus x squared. And it is at this point that you might either get stuck, give up, get confused, not know what to do, perhaps spend time or waste time trying to like do this integral or whatever by looking for an antiderivative of root a squared minus x squared. This is not impossible, but it is hard. But what you're really supposed to do is to, I think, what our book wants us to do, I guess, is just recognize this as the formula for the area of for a semicircle. In other words, interpret this green box as 1/4 of the area of a circle of radius a centered at the origin. So if you give me some circle now, so that's a comma 0 and that's 0 comma a, then it just is true that the area of that quarter circle is going to be the integral from 0 to a of the height of that thing. And since the equation of this circle is x squared plus y squared equals a squared, then the equation of this will be y equals root a squared minus x squared. And we're just kind of assuming now that we just already know the formula for the area of a circle, and therefore this is really like 4 times b over a times, well, the area of 1/4 of a circle of radius a is going to be pi a squared over 4. So that stuff in parentheses is just the value of the thing in that green box. And then the 4's cancel, one of the a's cancel, and we just do get pi ab. Whew. Okay. So an obvious question is, do I just have to accept this formula for the area of a circle, or now that I have calculus, are there like advanced techniques at my disposal to actually like prove using fancy techniques the formula for the area of a circle? Yeah, this can be done. I did it in the Friday afternoon Zoom call, but maybe it's not going to really change your life. See my Twitter for more details on this. Okay, good. That was section 7.1 on area. Now we have 3 sections to go on volume, and then we are done. Goodbye.